Can you hear me? I think you can probably hear me without this, to be honest with you. So, glad y'all are here this morning. I wanted to introduce Dr. Palke. Dr. Palke developed an interest, you probably heard us talking just a second ago, in minerals and gemstones early in life, searching for agates and other minerals in eastern Montana. And he became fascinated with the geographic distribution of minerals and gem deposits and the geological features that he came across, and just wondered why all of these things were occurring in Montana but not back in Oklahoma. Not a lot of things geographically other than flat and red clay, right, in Oklahoma. I came from Georgia, it's kind of the same. So those questions that he came up with really led to him pursuing his formal education in geology. He got a Bachelor of Science degree from the University of Tulsa, a PhD from Stanford, and then began his postdoctoral career as a research associate at the GIA, and he is now the senior manager of colored stone research. Sounds like dead center for turquoise. In this role, he leads GIA's research efforts into the geographic origin determination for rubies, sapphires, emeralds, and of course, turquoise. As well as improving criteria for identification of treatments for colored stones, he's a regular contributor to Gems and Gemology and serves on the journal's editorial review board. Welcome, Dr. Eric Palke, this morning.
Really interested in hearing the science about this. That's great.
All right. You all hear me? So thanks for getting up early and coming out to see this talk. I want to give a kind of an overview of what we do at GA in regards to turquoise. One of the things Joe Dan said to me when we kind of first met and were chatting last year is he said there's no experts in turquoise. And I wasn't quite sure I really believed him when he told that to me, because he, to me, was an expert in turquoise. The more I learned about turquoise, though, I think he actually probably really did mean it, and I kind of understand what he was saying about when he said that, and that there's this whole breadth of turquoise, this whole world of turquoise, and it's very difficult for any one person to kind of cover everything there is to know about turquoise. And so I make that point because I'm not an expert in turquoise. But at the Gemological laboratory, there is this huge area of intersection between your world of turquoise, which I consider you all to be kind of the experts in turquoise, and what we do. And I think there may be a little bit of what we do in the laboratory might be a little bit opaque, or maybe not quite well understood to some of you all in the trade, or the your turquoise enthusiasts. So I wanted to give an overview of what we do in turquoise, to understand how our two worlds intersect and what we can do together. So this slide here, I actually stole this slide from my colleague Wim Vertriest, Belgian guy who, yeah.
Should I turn this where it takes you and the screen?
Up to you. I mean,
they do it a different way. So the video actually records on the screen by itself.
Oh, okay. Okay, thanks. So I stole this slide from my colleague Wim, who's a Belgian guy who lives in Thailand. He's our field gemologist guy. He goes out, he's like the Indiana Jones of the gemology world. So he goes out to all the crazy places in East Africa and Southeast Asia looking for gemstones. But he put this together. He was giving this talk about, he wanted to kind of cover the evolution of the Gemological laboratory, how our focus has changed and how what interests us in the Gemological laboratory has changed over the years. So when GIA first started, the biggest question we had was identification. Is this a diamond? Is it not a diamond? Is it a pearl? Is it not a pearl? Pretty simple, basic questions. Although back in the day, without our advanced technology, sometimes it could be a little bit tricky. From there, as the economy, especially in the Western world, is growing, more and more people are looking for gemstones. More and more people want shiny rocks on their hands. So the supplies of gemstones grew as well, but not quite to the extent that we could cover everybody's needs. And so people also, with technology increasing, technology growing, people found ways to kind of game the system and treat gemstones in order to increase the supply of pretty stones that people could have, from stones that are coming out of the ground that don't quite look like they are when you put them on a ring on your finger. So we have these treatments to increase the properties, the qualities of gemstones. These are called treatments. We also had advances in laboratory-grown gemstones, or synthetic gemstones, around this time. So we had all these new gemstones being grown in the laboratory, also to kind of supply this need for more gemstones. And so over the decades after the gemological laboratories were first kind of introduced into the world, the focus started shifting to, is it natural? So did it come out of the ground looking like that, or was it tricked? Was it somehow enhanced by human beings later? And now finally, in our kind of third stage of what gemological laboratories are concerned with, we have this other question of where is it from? You all in the turquoise world know this, and it's probably a bigger question for the turquoise people earlier on than it was for other gemstones. But now a lot of our research, especially in color stones, is in origin. So is that ruby from Burma? Is it from the new deposit in Mozambique? Is your sapphire from Kashmir, or is it from Madagascar? These are big questions now in the gemological community. So why do we care about these questions at all? Showing here 3 red stones, all quite nice stones, right? Pretty. I'm sure you all can look at these 3 stones and have your preference for which stone is your favorite. Anyone to just say what their favorite one is? If you had to choose one of these 3, what would you choose? Not knowing anything else about them.
The top one.
The top one?
Lower right.
Lower right?
One in the center.
Okay, so we got one of each. One of you all is right, one of you is kind of right, and one of you is really wrong, because one of these is a garnet, one's a spinel, and one's a ruby. So, would you all change, if you chose the one on the top, would you change your opinion now?
Yes.
Right. You would have chose the one on the bottom. And so, knowing what the stone is obviously very important. This is a big part of what we do, and it's a pretty basic level of our identification reports, what we do in the laboratory when you send us stones. We tell you, is that red stone a garnet, a spinel, or a ruby? GIA doesn't usually talk about value of gemstones, so I'm not like saying that one is actually better, but we all know that in the market, there are these differences in prices, and so it's actually very important. Now the next part of this is, has it been treated? This is a sapphire that we cut in half to do some treatments on. The half on the left is the original state of the stone. The half on the right is the treated state. This is a treatment you may know of, is called beryllium diffusion. So you take a sapphire, a pinkish sapphire, you heat it up, and in presence of this trace element, this foreign element, beryllium, the beryllium diffuses into the stone at high temperatures and fundamentally changes the properties and the color of the stone. So we took this pink sapphire, turned it into a nice orange sapphire. This was really big in the early 2000s when people were taking pink sapphires, turning them into pod paracha-like colors. So pod paracha, if you're not familiar, is a peachy pink. So it's an orangey pink to pinkish orange sapphire. Very rare naturally, highly valuable, but we saw this flood of these stones in the early 2000s, and so there's just this new treatment that we identified as beryllium diffusion. So obviously, a beryllium diffused pod paracha like sapphire is not as valuable as the natural pod paracha, the very rare stone that comes out of the ground with those kinds of colors. And finally, we have this question of where is it from. This is a map of ruby distributions around the world, major ruby deposits. And so the basic question is, if I have a ruby from 2 different deposits, Mogoc and Mozambique, even if they look the same, more or less, they have pretty much the same qualities, the market puts a difference in value on those 2 stones. You all in the turquoise industry know this well. A ruby from Mogoc from Burma generally is valued more highly because of that provenance, because of the history and legend and lore of stones from that deposit. It's kind of a much more rare stone, it's a collector stone, whereas the rubies from Mozambique are produced in abundance. There's a lot of these stones. This is a modern deposit, so it doesn't have that history and that lore and legend behind it. And so, like it or not, origin is an important part of the question. So just a little bit more background about GIA in the laboratory, what we do. You may or may not have seen reports like this. These are actually pearls in this report, so it's not actually as relevant to you all, but we issue reports on gemstones, pearls, diamonds, colored stones. So you send your stone into us, you don't know exactly what it is, or you have a client who wants some assurance about what the stone is. So is this stone a ruby? Has it been treated in some way? Where is it from? You may very well know, but if you want to sell your stone a little faster, giving some assurance about what your stone is can really help a sale go. Can give some assurance to clients and to consumers. So we issue these reports based on the overwhelming experience of our gemologists and our advanced technological instruments in the laboratory to give some assurance to the trade about what's going on. And so I'm going to use this as kind of the backdrop of today's talk about turquoise. I haven't even mentioned turquoise yet, which you might be confused about, but we're getting there. So this is turquoise. This is kind of GIA's, the way GIA looks at turquoise in terms of our identification reports, that when people send in a piece of turquoise, these are possible conclusions that can be given to the turquoise. So at the top of the heap, obviously, is natural turquoise. So this is turquoise with no indication of treatment, has not been altered in any way. It was pulled out of the ground. At best, it was cut and polished, and that's it. So that's kind of the best possible outcome for you if you're submitting a turquoise to us, all other things considered and all other things being equal. And as we go down the line, we have all these other conclusions that we can put on our reports. So the next slots in there are natural turquoise, which has been treated in some way. And then following that are imitation, synthetics, and plastic. So without further ado, I'm going to just jump into it. We're going to go through these one by one. I'm going to give examples. Yeah.
On your screen, you have a filter warning. I'm not sure where that's from.
Projector, I guess.
Need the scanner, right?
It must be from the
Must be.
projector, right?
Yeah.
No, it seems to have gone away.
Good job, Craig.
Yeah, you didn't even need to hit it.
All right.
No standing ovation.
Thanks.
Oh, sorry.
So for the rest of the talk, pretty much, I'm going to go through these conclusions one by one, give some examples, show you what these things look like on the reports, and also give you an idea of how we come to these conclusions. So when we have a turquoise, what do we do? What tests do we run to know what's going on with the turquoise, to know what we're looking at? So the first one, like I said, the best conclusion, all things being equal, is that your turquoise is natural turquoise, and it hasn't been treated with, hasn't been fiddled with in any way. So this is only reserved for natural untreated turquoise, where the only alteration is cutting, polishing, a natural piece of turquoise. So no dye, no impregnation, no Zachary treatment, et cetera, et cetera. How do we do this? We talk about gemological properties in the laboratory. So gemological properties, things like refractive index, specific gravity, fluorescence, the way a stone looks. We also have advanced instrumentation that we use, FTIR spectroscopy, and I'll explain what that is in a minute. We may also use Raman spectroscopy. Alex touched a little bit about Raman spectroscopy yesterday, and maybe X-ray fluorescence, which is a way of measuring chemistry of these stones. So for natural turquoise, the refractive index is going to range from 1.61 to 1.65. So that's one of the first tests we do with almost any stone that's coming through the lab. We check the refractive index, because that automatically gives you narrows down your options for what you're looking at and helps you identify what you're looking at. So if I get an RI outside this range, even if the thing looks like turquoise, I'm going to be thinking about something else. The SG is generally around 2.74, but this varies with the amount of matrix that you might have in your stone. So SG is not the most useful thing for turquoise. More important, or maybe not more important, but things we use to confirm turquoise, especially is for FTIR spectroscopy and potentially other advanced instrumentation. So, yeah.
How do you get refractive index off a stone like that? You have pyrite in there, you have the matrix, you have the turquoise itself.
Yeah.
Where are you bouncing the RI off of?
So it can be tricky, but I'd want to find a spot which is more, more turquoise than not. So kind of like right in the middle of that stone, you've got a pretty good patch of turquoise there, and we do a spot RI. So you're only looking at we get a very small, the smallest drop of refractive index liquid as we can on the stone in a certain spot, and we do it. We try to get the region with the most turquoise. Now, if it's really more heavily included in this, I think I could probably get a turquoise RI off this. If it was more matrix mixed in there, then it might be difficult. And in that case, we would rely more on the advanced instrumentation. So FTIR, Raman spectroscopy would probably carry more weight in those cases.
And heavy liquids are going to damage the stone, so you don't do much of the specific gravity?
No, we don't really do much. Well, we measure specific gravity in some cases with just a water balance. So you weigh the stone, and then you suspend the stone in water, and you weigh it suspended in water. You can measure the specific gravity like that. But again, if your stone is heavily included, you have a lot of matrix, that's going to throw your specific gravity off as well. We don't like to play too much with the heavy liquids because they're kind of nasty.
Mm-hmm.
Yeah. Good question though. So for the advanced instrumentation, I'm also going to walk you through some of what we do with this advanced technique so you guys understand a little bit. I talked about FTIR spectroscopy. To talk about that, we need to talk about spectroscopy. Spectroscopy is basically just the science or the measurement of how light interacts with matter. So you've probably seen the electromagnetic radiation spectrum before, right? So we have In the middle, the important part for us is visible wavelengths of light. That's between about 380 and 780 nanometers of light. So nanometer is a very small, so 10 to the minus 9, one billionth of a meter is a nanometer. So incredibly small wavelengths of light. But these are the wavelengths of light that are visible, that interact with our eyeballs and create color, right? So from violet and blue in the short wavelength region to red in the long wavelength region. To illustrate this a little bit, I'm going to talk about color in turquoise. So turquoise is colored by the presence of the element copper. So this is an absorption spectrum. What you're seeing here on the horizontal axis from 400 to 700 nanometers, these are the wavelengths of visible light. And then on the vertical axis, that squiggly line you see, that shows you how much of the light at these different wavelengths is absorbed and how much is not absorbed. So the light that's absorbed is the light that's not going to be transmitted to your eyeballs. The light that's not absorbed is what's going to be reflected off this turquoise and transmitted back to your eyeballs so that you can see it. So we can see here this area of intense absorption. So where the line is high, where the squiggly line is high, that's where most of the light is being absorbed. And you see that's right in the red region of the spectrum. So that leaves what we call a transmission window, where the squiggly line goes down, and where all that light gets reflected back off the turquoise and gets transmitted to our eyeballs. And so this region where this transmission window is right there in the blue. And so that's why turquoise is blue fundamentally, because the copper is absorbing all of that red light, letting the blue light be transmitted back to us. Now we also have cases like this, where we have potentially a green turquoise. So when a green turquoise is colored by copper and iron. So we have in this region here in the blue and the violet, iron in the turquoise can absorb light very strongly there, leaving a transmission window only kind of in the greenish region of the spectrum. So the more iron we have in this, the more green your turquoise becomes. So I just use that as a fundamental kind of explanation of what spectroscopy is, because I'm going to show a lot of spectra, we call these spectra later on in this talk. So identification turquoise. This is really about identification of turquoise. How do we know something is turquoise or something else? For that, we turn to this part of the spectrum, infrared rays. So these are wavelengths that are longer than red wavelengths. We can't see them with our eyes, but they're still there. They're still all around us, and they're very important for identifying turquoise. This is what our spectrometer looks like for the infrared. I call it FTIR spectroscopy. FT stands for Fourier transform, and IR stands for infrared. Fourier transform is just a kind of a mathematical process for how we take the data that gets to the detector and turn it into an absorption spectrum. So that's not so important. We won't go into that too much here, but it's really an IR spectrum. And I'll try to just call it an IR spectrum from now on. But basically, we put our sample here in the middle there. We have mirrors all around that are transmitting infrared light into the sample, through the sample, and then out into the detector. And this is what it looks like. So the key thing here is that most minerals have characteristic patterns in the IR spectra. And we use actually a lot in the laboratory to identify materials, or at least get a very base level understanding of what the material might look like. For turquoise, it's quite important. So turquoise has this characteristic pattern, and this pattern is called, these absorptions are caused by vibrations within the turquoise. So the turquoise vibrates at specific frequencies in the infrared. When we pass infrared light through the material, it absorbs those specific frequencies and causing the squiggly line to go up. So wherever you see the squiggly line go up, those are specific vibrations in the turquoise that are characteristic and kind of a fingerprint to the turquoise that you're not going to see in other minerals. So we get our piece that we had previously, we get an infrared spectrum. It looks like this. We know it's turquoise because nothing else really looks like this. And so we can positively conclude that we're looking at a piece of turquoise. So again, we come back to the original conclusion. This is natural turquoise. Again, only from natural untreated turquoise, no impregnations, active treatment, dyeing, et cetera, et cetera. And so what we would conclude in the report, we'd call this the species natural turquoise, or alternatively, natural turquoise with matrix. The report would look something like this. You get a picture of the stone in the report, some of the dimensions we would call the color, the transparency, the way the stone is shaped or formed, and then importantly, in the results, the species is called natural turquoise. We have the one I showed you in the beginning with a lot of matrix in it. In this case, if you got a lot of matrix in your stone, we're going to have to call it because we really want to just convey information to the people, to whoever's getting the stone in the end. They need to have the information, all the information possible. So in this case, we would call it natural turquoise in matrix. So that was the most favorable outcome for you, right? So you send your stone into us, you hope that's what you're gonna find when the report comes back to you. Everything else is kind of like one rung down on the ladder. So this next one is gonna be natural turquoise with a statement in the treatment section of the report that says treated. And when we say treated, we're referring specifically to what we call the Zachary treatment. And so this also comes with a additional comment saying this turquoise has been treated by a proprietary process that decreases its natural porosity without using polymers. So that's shown in this photo here. You see the stone on the left, kind of a lighter colored stone, has not been treated. The stone on the right is a similar piece of material that has been put through this proprietary process, sometimes called the Zachary treatment process. And you see the colors change dramatically. What's going on? We don't fully understand at the GIA at least what this treatment really consists of. If anybody wants to tell me, I'm more than happy to listen to you.
Uncle Jimmy died a couple of weeks ago.
Oh, really?
Yeah, so there'll be things that are coming out, I'm sure, from the kids.
Okay, that'd be interesting. Well, we'll know more later, I guess. But what's happening fundamentally is this treatment decreases porosity in a piece of porous turquoise. By decreasing porosity, it decreases the scattering of light in the stone and creates a better color, so a deeper color, by reducing scattering and potentially also increasing the stability of the stone as well. So here's our example. This is a stone that came in for a report. All these stones I'm showing like this are actually stones that came in for reports. I took out all the kind of report numbers and all that stuff, so you can't really look it up later, but I wanted to just show you guys what actual examples of stones that came through the lab. So in this case, we call the stone, the species is called natural turquoise. We have a treatment section that comes up that says treated, and again, that additional comment I mentioned. So how do we identify Zachary treatment? Generally, it's not detectable by standard gemological analysis. So standard gemological analysis is specific gravity, refractive index, looking in the microscope, these sorts of things, fluorescence. In some cases, and they reported on this in the initial analysis in Gems and Gemology, in some cases you might see some color concentration along pre-existing fractures, but this is not really generally found, so it's not something you can really rely on, at least in our experience. In most cases, you don't always see these color concentrations along fractures. And in fact, I would say in most cases when we're calling Zachary treatment, we're not really seeing this sort of thing. We're basing it on other properties. So we had to turn to advanced analysis again. And in this case, we're looking at this technique called X-ray fluorescence. So X-ray fluorescence, or XRF, is a way of measuring chemistry. What happens here is, if you recall your high school chemistry classes, or if you don't recall your high school chemistry classes, I'll tell you about it. An atom is basically a nucleus with electrons going around outside the nucleus. So the nucleus is a positively charged part of the atom. It has positively charged protons, neutrons, and then swarming around the nucleus are negatively charged electrons. But the electrons aren't just kind of swimming around freely. They're in these discrete shells, what we call shells. And these shells also have specific energy levels. So an electron in the shell close to the nucleus is at a lower energy, and as you go up in the shells, further away from the nucleus, you go higher in energy. So X-ray fluorescence takes advantage of this by bombarding this atom with high energy X-rays. When you do this, you can knock an electron out of one of these inner shells, and this creates a vacuum. In nature, abhors a vacuum. So an electron comes from one of the higher energy shells and falls into place. But there's this difference in energy here. So we're going from high energy to low energy. So to compensate for this, that energy has to go somewhere. So what the electron does is it actually creates an X-ray of its own when it falls down into this energy level. So it creates an X-ray when it falls down to the shell, and it emits that X-ray. Now, the useful thing here is that each atom in the periodic table has its own unique signature of energy levels, which means it has its own unique signature of X-rays that are produced when we put it in this high energy X-ray environment. And so we can look at the X-rays being emitted from the sample and know which elements are present in our sample and which are not. So here's the instrument. It's pretty simple from a kind of a very general perspective. It's got an X-ray tube that aimed at your sample. Then there's a detector underneath your sample that just picks up the X-rays that are emitted from your sample after being hit by these X-rays. Actually, the nice thing about XRF is non-destructive. We can measure elements from sodium to uranium, essentially. We use it for some certain geographic origin calls in the laboratory. We look for certain treatments, and for laboratory-grown stones as well. And I'll show some examples. So this is the first example, just to kind of give a broad overview of what we do with this technique. This is an X-ray fluorescence spectrum of a lead glass-filled ruby. So just like people fill turquoise with polymers and stuff, people take rubies with lots of fractures, and they'll fill it with a lead glass, a high lead glass. This high lead glass is refractive index matched with the corundum, with the ruby, so you can hide fractures very well when you put these lead glass in there. So we do this pretty frequently in laboratory. We put a ruby on the XRF. If we see these big, large peaks, so PB stands for lead. If we see these big, large peaks here for PB, or lead, we know we shouldn't see that in a natural ruby, so we know that this is a lead glass-filled ruby. And so we also see in this photos, so these peaks here marked PB or lead. We have one here, GIA, which stands for gallium, one here for iron, which stands for, Fe stands for iron. So again, we have these characteristic X-rays for all the different elements in the periodic table that we can look for and know whether or not they're in our sample. This is kind of an example. So I mentioned we do origin determination sometimes with X-ray fluorescence. One specific example is Mogok or Burmese rubies, which have low iron, compared to Thai rubies, which have very high iron. I don't know if any of you all know Jim Shigley from the GIA. Maybe not, but this is a photo of Jim Shigley. Joe Dan, I think you met Jim in the lab.
He wasn't that young.
He wasn't that young, no. I like showing this photo. It's a really good photo of Jim at one of our older X-ray fluorescence images, X-ray fluorescence devices. So to kind of just a very broad highlight of what we do with this, this is a Burmese ruby. We see all these characteristic X-ray peaks. We see chromium in there. So chromium, rubies are colored by chromium. They're colored red by chromium. So of course we're going to have some in there. We see some titanium, potentially some vanadium, some gallium. Importantly, there's almost no iron in this sample. And we can contrast that with the Thai ruby, which has those same trace elements, but it also has the presence of a very strong iron peak in here. So we can very clearly distinguish at least these two broad sources of rubies according to their geographic origin based on the presence or absence of iron. Now, relating this to turquoise, we use this X-ray fluorescence device to look for the presence or absence of Zachary treatment. And what we look for specifically is this trace element potassium. We're not quite sure exactly what's going on with this process, but it does seem to significantly increase the potassium content of the turquoise that we're looking at. So if we see very strong potassium peaks, and specifically what we see, if we see potassium peaks stronger than the calcium peaks in a turquoise, then we know we're looking at a Zachary treated stone. In contrast to if we see very little potassium or almost no potassium, we know that stone has not been Zachary treated. So again, this is our example here, the stone on the top. If we see this high potassium peak like we saw in the spectrum previously, we know it's been Zachary treated. We call it natural turquoise with the additional comment, with the comment that it's been treated, and an additional comment saying this turquoise has been treated by a proprietary process that decreases natural porosity without using polymers. And so it's shown here, we see in the treatment section, it's called treated. That additional comment kind of gives you an idea of what's going on with this treatment as well. Right, so then the next thing we'll consider, if we put the stone and it's not got a Zachary treatment, we know that we don't see those potassium peaks in the XRF. One other kind of treatment we would consider is polymer treatment or impregnation. So shown here on the left are some untreated turquoise with kind of a chalky light blue color, and then on the right, not the exact same stones, but similar stones that would have gone under this impregnation treatment. And we can see a significantly increased color. These stones would potentially take much better polish depending on the type of polymer used in this case. They can kind of infill those pores and help you to actually polish the stone without it falling apart, depending on what material you're actually working with. How do we identify this? One thing we can do, and I remember Joe Dan at the panel I was in last year was discussing, I think probably simulated turquoise or imitation turquoise, and I think you said you could put it on a wheel and hit it and see if you get a smell coming off of it.
Right, great heat and it's, right, so
Yeah.
stabilized or any of those, you can't do it with in hands.
Okay, right, so we would use a similar kind of thing in the laboratory. Of course, we can't really put anything on a polishing wheel because our clients probably wouldn't like that very much. What we use are these hot ones. So it's like a little pen, you put a battery in it, and it's got a wire coming out the end that heats up when you press the button. And so we take this hot point and you gently introduce it to the surface of your stone,